All right. Hey there, AP Physics. This is Barry. I'm here to run through the Unit 0 notes for you. So they'll be posted on the website, but want to make sure that we talk through them so that you have me actually delivering them to you also. So we're going to start right here. This is our introduction unit. First thing I want to talk about are scalars and vectors. So a scalar is a quantity fully described by a numerical means. That means there's a number only. A vector would be a quantity described by both a magnitude and a direction. Now, the key there is that magnitude term. There is a magnitude with both of them. And you see that right there. Magnitude, magnitude, they each have a magnitude within them. That's important to notice. There's a number associated with both. But a vector has a direction that's associated with that number as well. A great way to note this is the difference between the terms speed and velocity. And that's something we'll cover more in Unit 1, kinematics. But a speed is something you would see on a speed limit sign. It has just a number. You're not supposed to go above that number, right? Not that anyone ever does. But a speed limit sign is a scalar. Now, something told to you by your GPS would be more like a vector. It's not just telling you, right? Within your GPS, it can tell you, okay, this is still the speed limit for this area, but now you need to turn right. There's a direction associated with that also. That's the big difference, all right? And that's why we see velocity over here as a vector quantity. So we see quite a few of these together here, and we note the big difference between them is those vector quantities have a direction, and the scalar quantities only have a value associated with them. When we talk about vector directions, it's important to note how we're going to talk about those directions. So there's really two ways to orient yourself and tell how the direction is changing. Number one would be your original orientation. So this is saying we've got this little guy right here. He's walking from A to B. As he walks from A to B, when he gets to point B, he takes a 90-degree turn to the right. Okay, that's all based on his orientation. If he had started walking up, then a 90-degree turn to the right would be making him move to the right instead of going from moving to the right to moving down. So the original orientation that he was at was really important for that. The other one would be the compass orientation, in which case we would say, all right, make a 27, like you're heading north, make a 27-degree turn towards the east. We would turn 27 degrees this way. So this guy right here would be going from A to B, he'd be going east, and then would make a 90-degree turn towards the south. So it's important to note that those are our two ways to determine those vector directions, and just make sure that you are saying things in some way that you can orient yourself and make sure that those directions are known. When we add vectors together, we're going to go back to our Pythagorean theorem and our SOHCAHTOA and all that fun stuff that you've learned in math in the past. So we do need to make sure that we can add those. We need to remember our sine, cosine, and tangent, and the fact that a plus b squared is c squared. Remember, that's only for a right triangle, okay? But just a quick reminder on all those things because we're going to be using them. And that looks nice and simple right there, but then we get to things that look a little bit more complicated because what we're going to want to do eventually is put vectors together. So we have vector A here being added to vector B, and we're using what's called the tip-to-tail method. So when we have our vectors, we can move them and orient them differently if we are adding them together. So I'm going to take the tail here of B and move it up to the tip of A, and now I have A plus B giving me C from the origin to where that ends, and that's the key there. All right, and we've made our triangle within ABC by doing that. And we've said then that A vector, so the amount that A goes up, AY, plus the amount that it goes right, added to the same things for B, the amount that B goes up, BY, plus the amount that B goes right, BX, now equals the total for C, that is CX in the X direction, AX plus BX, and CY in the Y direction, AY plus BY. And you see that outlined in these spots also. And that's your very basic vector addition. And obviously with numbers, it'll look a little different, but we'll get some practice with that. And let's actually look at a very quick example problem as we're doing this. So because a person cannot walk in a path that goes through buildings, they must walk 5 blocks north and 9 blocks east in order to get from a starting point to their destination. Someone's walking through a city. How many blocks would a person in a helicopter have to travel to go between the same 2 points, given that they do not have to worry about buildings? At what angle would the helicopter have to travel relative to the starting point? So we have 5 blocks north, so they're going up, is typically associated with north, 5 blocks, and east, that's typically associated right. So 5 blocks north, 9 blocks east, they are walking a total of 14 blocks. 9 plus 5, pretty simple right there. The key is we want to know how far the helicopter actually has to travel in order to do the same thing since it doesn't have to worry about the buildings. So if we take a look at this diagram, we see we've got that 5 blocks north and that 9 blocks east that it was going, but because it can go straight, it's going right here at this point. So we have our 5 squared plus 9 squared, and then take the square root of it, and we see the helicopter path is only 10.3 blocks. We got our hint SOHCAHTOA right there also, but remember that Pythagorean theorem also, a squared, b squared, c squared. I put the hint for SOHCAHTOA because that's how we find theta right there, right? Once we know all those signs, we can then solve for the angle that it actually had to fly at also, which is the second part of this problem that it asked. All right, so that's a very basic way that we're going to do that. We'll get a bunch more practice with vectors, but it should be something you've seen in class before. Now, directions in physics are very, very important, okay? So only two things matter when we consider direction, positive and negative. And that's really important also because positive and negative in physics also then just mean direction, okay? So we don't really worry about the positives and negatives so much as the direction that they're associated with. Here we have 2 positives, so we're moving at 20. Here we have 2 negatives, we're also moving at 20. So the 20 newtons combined in both those cases gives the same resultant force. The key is that they would just be pushing in a different direction. And newtons are a way that we measure force. We'll get to that more in Unit 2 dynamics. Here, because we have 10 newtons pushing both directions, our resultant is 0. A good example of that would be if I took my hands and pushed them together. Well, my hands aren't moving right now because I have a net force of 0, right? I'm pushing the same with both. Now, if I was pushing the same opposite there, I'm moving in one way or the other. And that's why we end up with our resultant forces like we had for these first two. Going to our vectors here, we have 10 newtons one way and 10 the other way. I'm not going to have 20 because we have to use vector addition like we just looked at to put these together and get that 14.1. And now the same thing here will be true. We'll have 14.1, so the scalar values will be the same for both of those, but our vector values, our actual specific directions will change because we actually now don't just have a scalar, we actually have a vector value going on there, right? So we are beyond just the scalar at that point. And now when we have these two angled forces here moving in very different directions, those combined based on the angles that they are at can have the same magnitude but going in a different direction. And I think that's very important to note because that's something that can be very hard to see and understand on your own. But it's the combination of these that make them result to have the same thing, okay? So that's important stuff for our directions right there. Really, really important to note. Positive and negative in physics are just direction. And note, right is typically considered positive, left negative, up positive, and down negative. So things to remember right there. I want to briefly hit this give and find solution method for solving problems, and you'll have a homework that'll get a little more in depth into this, but we're going to solve our problems using a 3-step method in physics, and you may not write it out for every single problem, but if you ever get stuck on one or you get an in-depth problem, it's very important to be able to do this. So step 1, given right there, and you see it written out here for this problem. Given is step 1, just note what you are told in the problem. And that seems really basic, but in AP Physics in particular, there's going to be a lot of small things that are tough to see sometimes. So we're going to make sure that you see all those things. We write them all out in the given part of problems, and we'll get a lot of practice with that as we get into it. But very first thing we want to note is everything that we are given. The next step there is find, and this is usually a pretty quick one, but it's what is the problem asking for? What do we need to determine? Now, what's really important here is there might be more than one thing that we actually need to determine. If we are asked to find A, well, we might need to find B and C first before we can find A. So in our find step, we would want to note A, B, and C because we would need those other items in order to get to the end. And then step 3 here, plug and chug, we're going to use our equation sheets and all the values that we've listed out there to find the right equation and just plug our numbers in then and chug until we find a final answer. Okay, we'll get a lot of experience with that equation sheet too. And speaking of which, we're going to look at that a little bit. So the equation sheet is in the unit folder for this unit, but I kind of broke down some of the basic parts here. So you're going to want to probably pause this real quick, pull that up, reference it, see it on a bigger scale so you can see what's going on. But there's some portions of your equation sheet that I want to point out because they're really, really important. And I tried to color code here to make it as easy to see this as possible. This is the biggest resource you'll have for this class. Know that those equations will be with you on all tests, on all homeworks, on all labs, on your AP test. Will be given to you all the time. You are not expected to memorize any equations. You might through practice, but you don't need to. All right, you're going to identify some parts of the equation sheet here. Now, on page 1, up at the top, there are quite a few given quantities. If you're ever like, I need to plug a number in here for, capital E, but I don't know what the heck that is, look here because it might be a given quantity, right? G is a value that you will get used to and you will know it is negative 9.8. It is the acceleration due to gravity. But if you forget it, if you have a brain fart on the test, you can always check right there for those given quantities. It'll be there. The next are unit symbols. So if you see a number with an abbreviation after it, and you can't remember what that unit means, you can always check right in there. It gives you your unit symbols there. And the bottom left of that first page, you have your prefixes. Nano, pico, mega, all that stuff, they're all listed there with the order of magnitude of 10 that's associated with them. So make sure that you realize you don't have to memorize those for this either. You might have memorized those in chemistry, but you don't need that for this. They are given to you. All right. Now, the rest of that is other stuff that will be useful too, and we'll talk more about that as things develop. But the really important things I want to point out now, we're going to flip to that next page of your equation sheet. And you're going to note you've got all your equations on the left, and everybody tends to just look at those and try to figure out what they need. But remember, on the right, it tells you what each of those terms means. That's really important. If you see the equation and you don't remember what one of the letters in the equation means, you can check the terms that are defined right there to the right of the equations. So always check that out. Make sure that you've got those down. And then finally, at the very end there, you have geometry and trig reminders. So it gives you some of those reminders there as far as finding some volumes, as far as your SOHCAHTOA. I remind you of that. I say that a lot. We'll talk about that a lot as we get through solving these problems, but know that it's on your equation sheet too, and so you'll always have that given to you also. The last thing I want to look at is how to evaluate some of those equations, okay? It's important to understand why they work. That's the biggest thing that we need to understand conceptually in physics. It's not just how to do the math, that is important, but we need to understand why these things work to help us do the math. So I put here one of our kinematic equations. And while that looks complicated right now, I promise you it will get easier as we get going. I want to note a couple things with this to get us started real quick, okay? So first, this little zero. We see an x and then we see an x0. That's referred to as x naught, okay? And that this would be v naught. And what that really means is it's at the starting point where the time equals 0. It's before we've started doing anything. So what this equation is telling me is x is its position, v is its velocity, and a is the acceleration of an object, where t is the time. And I should add that because that should be on there. Apologies for that. There we go. Now we have the time listed. We're going to be able to use these quantities all together to solve for one of those that we might not have. So what this one's set up is my position. Where am I? Well, that's going to be based on where I started, my position at time 0, what velocity I started at, my velocity at time 0, and how long I was going at that velocity, and my acceleration, if my velocity changes, if I speed up, if I slow down, and how long I'm accelerating for. T there also, okay? So we can kind of see all these things working together, and we're going to plug numbers in, and we'll get to that. We'll talk about kinematics and all that. You don't need to worry about solving these types of problems right now, but I want you to see that this works, okay? Because right now it's kind of like, how is that really going to give me a position at the end, like some distance that's actually going to work here? So let's look and see how that will actually happen, okay? First, position is in meters, velocity meters per second, and acceleration meters per second, or meters per second squared. Those are our basic units for this, and again, we'll get more into that in kinematics. Time in seconds over here, we see time in seconds getting plugged into. The way we do a unit analysis for an equation to make sure that it works is to note the units. Man, oh man. Apologies for typos here. For the quantities on the left, so we've got our units right there. We're going to plug those in for each of the quantities, okay? So instead of x, well, x is measured in meters, I'm going to put meters. X measured in meters. Velocity, meters per second, times seconds. I'm just plugging in the units for each of those different quantities. Any numerical values, like this 1/2, just becomes 1 because it's irrelevant for a unit analysis. We're not actually trying to find a final answer here. We're just trying to make sure the units will work. And so I would just plug in 1, so just to get rid of that completely. And then I'm going to simplify all parts here as we go through this, okay? So now I have I have meters per second there for velocity, time in seconds. 1/2, that goes away, it just becomes the 1. Remember, acceleration, meters per second squared, and then I have time in seconds, but that's squared. So if we look at what's happening down here, I got just meters and just meters. Meters per second times seconds gets rid of those seconds. And then meters per second squared times seconds squared gives us meters are going to equal meters plus meters plus meters. Well, My final position then will be where I started, plus how far I traveled based on my velocity, plus how far I traveled based on any acceleration. That combination of distance will then equal where I ended up there at the end. So that's our basic intro here. We'll get a lot more into these concepts as we do some homework and some labs and some simulations and all that stuff, but I hope that's helpful.